Everybody, it's video notes 7.2, take 3. So here we go. This time it's going to read chapters 10 and 14. Substances change temperature differently depending on their identity, and so we call that ability specific heat capacity. We use the letter C. The units for specific heat capacity are joules per gram degree Celsius or calories per gram degree Celsius. So let's talk about what it means. So if you're standing in the summer on the cement or the grass, which one feels hotter? Well, it's the cement, because the cement transfers its heat more quickly into you. Because cement has a lower specific heat, grass has a higher specific heat. So a high specific heat means it transfers heat slowly, so it would be more calories per gram degree Celsius. Right? Metal rack in an oven. Put your arm in there. You either got to grab the bar or just keep your arm in the oven. The oven air, the air in the oven will have a higher specific heat and not transfer heat as quickly. The metal rack has a lower specific heat, so the heat will transfer quickly into your hands because heat flows from high to low. Heat transfers from high temperature to low temperature, and so your hand's going to be the low temperature, but the metal rack transfers it more quickly, which means it has a lower specific heat. So heat and temperature are two different things. Remember, make sure you know that we use a thermometer to measure temperature, right? And that's just a detection of the movement of heat, and its average kinetic energy. Heat, we're not going to be able to use one instrument. We're going to have to use a technique called calorimetry. Where we take some data, and based on the data, we can figure out the heat transfer. So what kind of data do we have to know? Well, we have to know specific heat capacities. All right, so that's all three of these, which you have this sheet. And that only works if it's a single state of matter. So in another way to calculate heat transfer is to know about phase changes, and that's what these are for. So these are delta H's for different things. And you have to know the melting and boiling points of substances so you can tell when it's going to phase change. Here's another set of data, but this time the data is in joules versus being in calories. So these are all specific heats again, but this time it's joules per gram degree Celsius. And those are for single states of matter being able to change temperature. Here's some melting and boiling points so you know what phase it's in. And here's your delta H's. So we're going to be mostly, for these calculations, staying in a single state of matter. So it's either going to be here, here, or here. So here, here, or here on your graph, we can use this equation. And the Q is the heat. The heat is measured in calories or joules. M is the mass. Mass is measured in grams with the symbol G. And C is specific heat. That's what we were just talking about, specific heat. Because it's different for every substance, we could either calculate it or look it up. And that's calories per gram degree Celsius or joules per gram degree Celsius. The heat unit is the calories and the joules, but then we have to compare it per gram per degree Celsius. And delta T is a change in temp. And then, so you have two different temperatures, and their difference is their change, and it's going to be degrees Celsius. Okay, so let's see if we can apply it. What are we trying to find in this problem? Specific heat capacity of iron. Find E for C for iron, specific heat capacity. What do we know? What are we given? We're given that the mass is 15.75 grams, and we're given that the heat, the Q, is 1086.75 joules. And we're also getting that the temperature goes from 25 to 175 degrees Celsius. So the change in temperature is 150 degrees Celsius. So what do? We use this equation. Use Q equals MC delta T. Okay. So what is the Q? The Q is 1086.75 joules. The mass is 15.75 grams. The C is what we're looking for. And the temperature change is 150 degrees Celsius. So we got to get rid of the 15.75 grams and the 150 degrees Celsius. Goodbye, goodbye, goodbye. So now we have C equals 1086 divided by the 15.75 divided by the 150. Okay. So it's joules divided by grams divided by Celsius. And then when you calculate that, you get 0.46 calories for every gram degrees Celsius. So it takes, oh, I said calories, but is it calories? Heck no, it's not calories, Harbin. It's joules because that's the unit we were given. So that is a specific heat of iron based on this calculation. Okay, calculate the heat change associated with cooling 350 grams of aluminum from 70 to 25. Is it exo or endothermic? So what does this mean? Well, we're going from 70 degrees to 25 degrees. And it doesn't say, well, we don't know if it's going to change phase. So we go back to our data, and we look for aluminum, and we find out it doesn't melt till 660. So if we're at 70 and 25, it's going to be solid the whole time it's cooling off. Okay, so it's cooling off and it's solid. So now I know I can use the specific heat of solid aluminum. So what am I trying to find? Heat change, find Q. What am I given? I'm given its mass, it's 350 grams. Its temperatures are 70 and 25. So the change is 45 degrees Celsius. Okay. And then I looked up the specific heats of aluminum and then found out it is 0.92 joules per gram degree Celsius. Okay. How did I find that? Well, I looked for solid aluminum on the pink data sheet. So now I can use the equation Q equals MC delta T, plug it in, and I'm looking for Q. So I need the mass, 350 grams. I need this specific heat, 0.92 joules per gram degree Celsius. And I need the temperature change, 45 degrees Celsius. Goodbye Celsius, goodbye grams. Hello joules. Hey, that's what we're looking for. 14,490 joules is the amount of heat in this process. But is the aluminum losing the heat or gaining the heat? Well, the temperature goes down. So what happens to aluminum? Its molecules slow down. Right? The molecules slow down. So the molecules are slowing down. It's losing heat. So this is an exothermic process for the aluminum. Aluminum loses heat. That's exothermic. It's leaving. Okay. How do we detect heat transfer? Well, we did some problems and said there was heat, but how do we do that? Well, you have to use two systems, one system and the other. So total, the heat loss from one system goes into the other. Heat loss equals heat gain. See it again. Heat loss equals heat gain. Heat loss from one system equals the heat gain from another. So we use this technique called calorimetry. And here's an example of how we can use it. We could take a hot piece of metal, take its temperature, and then throw it in some cold water, take the temperature and the mass and everything about the substances to figure out how much heat gets transferred. Because the heat from the water, because water is going to gain heat when the hot metal goes in, it's going to be equal to the heat lost by the metal. So the water gains the heat, the metal loses heat, so heat loss equals heat gained. So if we calculate one, we know the heat of the other. Or we can calculate any of these variables, setting them equal. This works for chemistry. Woo! We can do a chemical reaction inside a little container, and then heat loss or gain in there. If it's lost, it'll go out into the water. If it's gained, the water's heat will come in. And so we can figure out how much heat the water loses or gains by taking its temperature and weighing it. And then, wow, heat loss equals heat gain. Key idea. Okay, so here's an example. The example for this is to find C of the metal. What is the specific heat of a metal? I don't know. But hey, you're going to have to do that in class. You're going to have to find it, and you have to come up with a way to find it. So let's look at what we have. We have water here. Water's going from 20 degrees, 0.1 to 24.1 degrees. Water's temperature is going up. Okay, I know I can use MCAT for this because it's a sign of mine. What happens to the metal? Well, the metal starts at 98.9 degrees and it goes to 24.1 degrees. So the metal's temperature is going down. It doesn't say anything about melting, so we'll assume it's a solid because it's a metal. Water's a liquid here. So we can figure out the heat here, we know the heat there. So we're looking for Q, and we know the mass of water, 37.5 grams. And we know the specific heat of water is 1.0 calorie per gram degree Celsius. What equation am I using? Q equals MC delta T. All right. And we know the temperature change is 24.1 to 20, so it's a 4 degrees Celsius temperature change. So we find out that the heat lost by water, sorry, it's not lost. Water is actually gaining the heat. Water gains 150 calories here. We're to get the heat from the metal. So we found the Q for this, which is the Q for that. Yay, we can use it again. Q equals 150. Why? Because that's how much heat the water took in, so that's how much heat the metal gave off. What are we trying to find over here? Well, we know the mass. So we know the Q is 150 calories. We know the mass is 86.2 grams. How do I know? It says right there. We don't know the C. That's what we're looking for. But we do know that the change in temp is 98.9 minus 24.1. So it's 74.8 degrees Celsius. Plug that in right here. And then what happens? Well, we got to get rid of this stuff. 86.2 grams, 74.8 degrees Celsius. Goodbye, all of this cancels out, but I have to do the same thing on this side. 86.2 grams. It's fun to think about it. 74.8 degrees Celsius. None of the units cancel when I do the math, so my units are going to be calorie for gram degrees Celsius. And then when I divide that all out, I get 0.023. So that is the specific heat of this metal. I just found the specific heat of a metal because I measured its temperature, measured its mass, put it in some water, measured its mass and its temperatures. Notice the final temperature of both of them is the same. That's how you know heat is done being transferred, is the temperature of both things ends up at the same temperature. Okay, one more time with calorimetry. This time, we want to find final temperature of the system. So both things together, what's their final temperature? Hey, what's cool about that is it's got to be equal at the end. So we have Q for a metal. Okay, so we have the heat of a metal, and we have heat of water. Okay, so heat loss from the metal is going to be equal to the heat gained from the water. So let's figure this out. Let's plug in the all of this stuff on the left side is about the metal. Okay, let's see what happens to the metal. The metal is going to start out at 100 degrees Celsius and go to some final temperature. I don't know, but it's going to do that. That's the metal. Over here's the water. The water is going to start out at 22 degrees Celsius and go to some temperature. I don't know. It's probably still going to be water, so it's like that. But the heat from this equals the heat from that, and X is the same. Woohoo! Okay, they're the same because they stop. When the heat stops moving, temperature gets constant. So the mass of the metal is 350 grams. Specific heat of the metal is 0.107 calories per gram degrees Celsius. And then the temperature change of the metal is 100, and it goes down to X. I don't know what X is yet. That's what we're trying to find. What about the water? Well, the mass of the water is 450 grams. Specific heat of water, it doesn't tell us. But if you look on your pink sheet, calories per gram degrees Celsius, it's going to be liquid H2. And then this is where it gets different. The temperature of the water is going up, and when you subtract it, so we need to know what the water goes up to, and we need to know what the metal goes down to, but X is the same. Okay, that's important, the way you put it in there, because look, water's temperature goes up, so the X is higher. Metal's temperature goes down, so the X is lower. So you multiply this out, you get 37.45 is 100 minus X. So 3,745 minus 37.45X. Okay. On this side, we got 450 times 1 times X. We got 450X minus 450 times 22 is 9,900. Okay. So now we just solve for X. So I'm going to bring over 9,900 plus 9,900. So I get 13,645. Then I'm going to add 37.45x to this side, so this goes away. And then add, so that goes away. I'm going to add 37.45x to this side. So I find out that 13,645, sorry about that, I I did my math early. Just write it down. Gives me 487.45x. Now I solve for x, and I find out it is 27.99 degrees Celsius. What does that mean? That means the metal ends up at 27.99, and the metal ends down at 27.9, when the water ends up at 27.9. This is the final temperature of the whole system. Woo, fun times. Heat loss equals heat gain. Please read chapters 10 and 14. All right. Now, also on this page, I want to show you graphs. Okay. Up, over, up. If you want to calculate heat for this graph, you have to use Q equals MC delta T here and here, but it has to be a specific heat of maybe solid and liquid. Okay. But then here, you have to use Q equals M delta H. But then, since that's solid and that's liquid, that would be the heat that it takes to turn a solid to a liquid. So you have to use a the heat of the phase change for that state of matter. So make a graph. Make a graph. We saw we make several graphs in here, so you make graphs too. All right. Remember, math is fun. Heat loss equals heat gained. Know your equations, draw your graphs. Peace out.